everyone, welcome to lecture 20 of AREC 333. Today we will continue with multi-output production, or more specifically two output and single allocable input production. So the plan is to finish this section today. We will first continue with revenue maximization, and if you solve the revenue maximization problem, then you actually get the optimal output combination. And after that, as always, we will do a profit maximization problem. And if we have time, I will do a summary of both the technical and the economic aspect of production winners. One input, one output, two inputs, one output, two outputs, one allocable input. And if we don't have the time, I will leave that to next lecture. So the readings here is the same as last time, so I will skip that. And let's actually move to the optimal combination of outputs. So from this name, you can tell that there's multiple or at least two outputs, and you need to find a combination that is optimal. So what is optimal? And for to find, remember, for the optimal input combinations is where when we have two inputs and one output, we will do a cost minimization. We said the optimal input combination is where if you are giving input level, if you are giving a output level, then the optimal input combination will lead to least cost. So here, in terms of the optimal combination of output, the optimal combination actually will maximize the revenue. So let's, I think we covered this last time, which is the a little bit summary of what we're gonna do. And we stopped here last time when we explained what's the optimization problem and what is the ISO revenue line. And I did draw in the graph, what is the slope of the ISO revenue line. Here, the slope is minus P1 over P2. And I think I did something wrong last time. So if the slope is minus P1 over P2, then Y2 should be on the vertical axis and Y1 should be on the horizontal axis. So if that's the case, you draw ISO revenue line, then the slope of this ISO revenue line is minus P1 over P2. So for a firm to find out the optimal combination of output, similar to the optimal combination of input case, there's something that's given. So when there's two inputs, one output, it's the output level that is already given. And back to our current case where there's two outputs and single allocable input, then we assume the input level is already given. So if the input level is already given, then the producer's problem is intuitive to think that the problem is try to get as much revenue as the producer can get. So we have that max total revenue, which is defined as P1 times Y1 plus P2 times Y2. So once there's only one output case, we simply write total revenue as P times Y. And now we have two outputs, so we have to give them subscripts for that. So what is the revenue maximization problem in the graph? So in the graph here, I already have the ISO revenue line, and what I need to do is draw another curve, which is what we covered in last lecture, is the product transformation curve. So remember the difference between the product transformation curve and isoquant curve. So isoquant curve, your slope is like this, and it's convex to the origin, while for the product transformation curve, typically it will have this shape where it's concave to the origin. So let's say this is your product transformation curve. And in order to max revenue for this given product transformation curve, so for each product transformation curve, the input level is given. So let's say this is X1. So this is a given level of X1. Then the producer is trying to find the max revenue that he or she can get. So assume there's multiple ISO revenue lines. The producer wants to get maximum revenue, and while at the same time it's feasible to produce by this level of input. So let's say this is revenue 1, this is revenue 2, and this is revenue 3. So there's 3 revenues there. At revenue 1, the producer with the input level of X1, can the producer get R1, revenue 1? Yes, at this point I just wrote here. So however, the producer can get a even larger revenue here at this point. So the producer with the same level of input, same level of X1, the producer is actually able to get a larger revenue R2. And can the producer get the revenue of R3? No, right? So it's because it's not possible to use the level of X1 to reach revenue 3. So revenue 3, R3 here is not feasible. And the maximum revenue actually happened here is where when the slope of the ISO revenue line, which is the slope is minus P1 over P2. And that slope is actually equal to the slope of the product transformation curve. So what is the slope of the product transformation curve? And that is actually dy2 over dy1. And we learned from last lecture that this is actually the rate of product transformation is actually equal to the negative of that slope. So remember here, both the slope of the ISO revenue line and the slope of the product transformation curve, they are negative because they're downward sloping. However, we usually prefer a positive number for the rate of product transformation or rate of technical substitution. That's why we put this negative sign there to make sure on the right hand side we're getting a positive number. But again here, so the optimality condition is where the slope of those two of the line of the ISO revenue line and the product transformation curve, they are the same. So, or you can say another way, they're tangent to each other. Then that's the point where you will find out the maximum revenue for a given level of input. And here, if we use this condition, we actually find out one point where the revenue can be get for a given level of input, right? And if we were actually given a different level of inputs, for example, if it's here, then we can also find another point of revenue maximization where the let's assume this is X2. So for another given level of input, we can also solve the revenue maximization problem. And this is the point of revenue maximization. And we can solve a bunch of different points of revenue of the maximization. And then if we connect all those points, then we get the output expansion path. So this is to differentiate with expansion path. So if we only say expansion path, that means we are finding out the optimal input combinations so that the cost can be minimized. And if we are having multiple outputs like it here, then we will say we will find out the optimal combination of outputs so that the revenue will be maximized. And then we will call this output expansion path. Geographically, the condition for revenue maximization is that the slope of the product transformation curve is the same as the slope of the ISO revenue line. And we can also write this condition mathematically. So here, this dy2 over dy1 is the slope of the product transformation curve. And this minus P1 over P2 is the slope of the ISO revenue line. So those two equal to each other, you will find the point to maximize revenue. And we can also write these two slopes a little bit differently. So first is, as we have just mentioned, the negative of the rate of product transformation is exactly dy2 over dy1, or you may say the definition of RPT is the negative of dy2 over dy1. So that's one way. And if you remember, we said that along one product transformation curve, the input level doesn't change. So that one equals to W1 dy1 plus W2 dy2 is equal to 0. So this means that we're moving along one single product transformation curve. Then from here, we can actually get dy2 over dy1 is equal to the negative of W1 over W2. So again, here, this subscript there means it's taking derivative. So that's taking derivative of the product transformation function, where x1 is written as a function of y1 and y2. So the w here means it's a function. So this is similar to the f that we have been used for production function. So here I just use a different letter to denote that this is a function. So again, this W1 means is d x1 over dy1. So that's W1. And as we mentioned in last time, this is actually equal to 1 over dy1 over dx1. And dy1 over dx1, we actually know that, and that is MPP, the marginal physical product of x1 and y1. So this is your W1 here. So your W1 is the partial derivative of x1 with respect to y1, and that is equal to 1 over MPP x1 y1. So that's your W1. And similarly, you can also find the expression for W2, and if you put them together, and you have to pay attention here, this is W1. So the subscript 1 is on the numerator, and here it is y2, which is on the numerator. So it's a little bit different. And that is equal to minus P1 over P2, and that's a slope of the ISO revenue line. So this together is the optimality condition. Usually we only use this part, and we can actually get rid of the negative sign there. So that's your optimality condition. But you do have to understand where those ratios come from, what do they represent. And here in the two output single allocable input case, I skipped the math that you can get this condition. I simply use the geographic interpretation and get this condition. When we had two inputs and one output, we actually used the Lagrangian function, and we used the optimality conditions there to derive the optimality condition. So when there's multiple inputs, or there's two inputs, the least cost combination of input, the optimality condition is actually R1 over R2 equals to MPP1 over MPP2. So for that condition, we use the Lagrangian method to derive that condition. Here, we can also use the Lagrangian method to derive this condition. And the steps will be similar. And if you're interested, you should go over that step and you will end up with this optimality condition. So since it's basically the same step, so I will not do them here. However, you do need to know this optimality condition. And if you're asked to do a revenue maximization in either your assignment questions or in your exam, it's okay that you just write out this condition, but you do have to understand what you're doing with that condition. So let's actually put this condition in a little bit in a little bit different way so that it has a different economic interpretation. So we have mentioned that this is the condition, the optimality condition, when you have two outputs and your input level is given. So for each given input level and you use this condition, you actually can find the point where the revenue will be maximized. And we can actually rearrange the terms of this condition. So we can take the product of those two, and given the equality condition there, we will know that this P1 times MPP x1 is this term here, x1 y1 equals to P2 times MPP x1 y2. And you have to recall what is actually the P times MPP. So we actually used this condition, or this is actually one of the concepts that we covered earlier in this course, is what is P times MPP? So we know MPP is a technical concept. And here, throughout this course, we use the letter P to denote the output price. So the output price times MPP is actually what we have used for a while. It is MVP. What is MVP? So MVP is the marginal value of the product. Or here, under the perfect competition, it is also equal to VMP, which is the value of the marginal product. So under perfect condition, those two are the same, and you don't need to worry about that. So P times MPP is the value of the marginal product. And again, here it's the same concept. It's also MVP. It is just you need to be careful about the subscripts. So let's actually do it a little bit slow here. This one means that P1 is the price for the first output. So P1 is the price for Y1. So previously we only have one output and we don't have this subscript. We simply have P as output price and Y as the quantity of the output. But now since we have two outputs, so we have to differentiate them. So here P1 is the price of the first output. And MPP x1 y1. So this is why I explicitly write the x and y here so that it's clear. So MPP x1 y1 is actually dy1 over dx1. So it's the marginal product of y1, so the first output with respect to the input x1. So that is the MPP x1 y1, and on the right it's similar. However, everything is for the second output. So the optimality condition is saying that MVP x1 y1 is equal to MVP x1 y2. Excuse me. So what does that mean? So this is actually a very important principle in economics. So this is called equal marginal return, which means that if you increase your output by a little bit, then since you have two outputs, where at which combination of those outputs will you maximize your revenue? It is actually where the return, the marginal return you got from those two outputs are exactly equal to each other. So that is the point where your revenue will get maximized. So again, you have to bear in your mind that this condition is when your input level is given. So for each, so if we put this in the graph, y1 and y2, and this is your x1. So that is along that one single product transformation curve. Along that curve, if you want to find a combination of y1 and y2 to maximize your profits, then you use this condition. However, if your input level change, then your revenue maximization point will also change.
This is the equity marginal return principle that I just mentioned to you. Is the MVP of Y1 and Y2 should be the same in order to maximize revenue. So here I actually have it written down in words, and I mentioned the farmer, but it could be the producer, the firm, or whoever. So it should use the inputs such as the last physical unit. So here, this last physical unit, it can be an infinitely small unit of that input. And then that infinite small unit of the input returns the same MVP for those two outputs. Or sometimes we also call those outputs enterprise. So for example, you're producing weight, that can be one output or one enterprise. And if you are having livestock, cattle, and that could be another enterprise. And it's very often that producers will have multiple outputs or multiple enterprise on the same land. Let's actually do an example so that you can get familiar with this revenue maximization better. And here I have give you a product transformation function. And let's actually use this function so that we can derive the optimal output combination to maximize revenue. So the first step when you're giving a product transformation and you're asked to maximize revenue, then the first step is figure out what is the optimality condition. And we actually have just mentioned that the optimality condition is the ratio of the output prices is equal to the marginal physical product, and this is x1, y2, and here we are having x1, y1, or you can just write it as what we have just mentioned, the equal marginal return principle, P1 times MPP x1 y1 equals to P2 times MPP x1 y2. So those two conditions are equivalent, and once you have that condition, then usually if this is a assignment question or an exam question, then I will give you P1 over P2. So that information will be given. And what ended up is that you have to find out those two expressions. What's the MPP? X1, Y1. So the definition of MPP is the derivative of the output with respect to the derivative of the input. So it is the marginal physical product. So if you increase your input a little bit, then what is the increase in the output? And here we add the subscripts, and there's only one input in our case, which is x1. And here, since we have that in the subscript, so the derivative should be dy1 over dx1. And what is that? That is, we mentioned, equal to 1 over dx1 over dy1. And if that's the case, we actually know what is dx1 over dy1 from here. So actually, the dx1 over dy1, I actually should write it as a partial derivative. So let's actually write it here. So the derivative of x1 with respect to y1, that's easy. So it's just 2 times y1, right? So MPP x1 y2 is 1 over 2 times y2, right? So the optimality condition is, let me write it here. So this is 1 over 2 y1. This is 1 over 2 y2, and I can get rid of this part of the board. And so the condition will be P1 over 2y1 is equal to P2 over 2y2, and you can actually write y2 as a function of y1. We can get rid of this 2. It's the same on both sides. So y2 will be P2 over P1 times y1. So this equation here is actually the output expansion path. So remember, in the 2 input case, we also have the expansion path. We actually solved the expansion path for Cobb-Douglas production function, and we mentioned there that if the production function is homogeneous, which in the case that Cobb-Douglas is homogeneous, then we have a linear expansion path. So that's for the 2 input case. So here, and this is a 2 output case, and you can see here the output expansion path of this type of the production transformation function is also a linear function. So once we were able to write y2 as a function of y1, we can plug this back into the product transformation curve, transformation function. So we can write x1 equal to y1 square plus y2 square, which is p2 over p1, and y1 square, and this is equal to p1 square plus p2 square, and then times y1 square. So we will be able to derive y1, which is, so let's actually write y1 square first, is p1 square over p1 square plus p2 square, and times x1. So y1 equals to this taking square root of this whole thing. So it's p1 times square root of x1 over p1 square plus p2 square. So that is our y1. And usually in assignment or exam questions, this input level is also given, so you can just, if it's a number, for example 10 units or 20 units or some other units, then you can just replace the number there. And y2, we can just use the output expansion path, is p2 over p1 times y1 times p1 times square there, x1 over p1 square plus p2 square, and we can actually cancel this p1 here. So y2 is equal to p1 times the thing in the square root. So that is how you can solve for the optimal output combination. So those two are this y1 and y2 are the output levels of those 2 outputs that will maximize the revenue.
The relationship between revenue maximization and profit maximization when there's 2 outputs are actually analogous to the relationship between cost minimization and profit maximization when there's 2 inputs. So similarly, when you have multiple inputs, you have your isoquant curve, and then for each isoquant curve, or you say for each output level, then you find a cost minimization point, right? So you can connect those points, that's your expansion path. And we know for each point, it's a cost minimization point. And along this path, there will be one point, one particular output level that will lead to profit maximization. So profit maximization point must be a cost minimization point. However, there are potentially infinitely many cost minimization points, and not all of them, or actually only one of them is profit maximization point. So in the output case, multiple output case, it's actually very similar. So we have this one product transformation curve, and then we find out the points where the product transformation curve and the ISO revenue line, they are tangent to each other. That's one point of revenue maximization. And we find another curve and another tangent points. And we connect all those points, that's our output expansion path. And again, also along that expansion path, there are infinitely many revenue maximization points. However, there's only one point among all of those points, that is the profit maximization point. So we had to find out which point among those revenue maximization points is actually the points that will maximize profit. So here I have the profit maximization point written here. So you're maximizing your profit. Again, we're using the letter pi to indicate this is profit. And we here we are having two outputs and we only have one input. So for these two outputs, the total revenue we have already learned is P1Y1 plus P2Y2. And we actually have to deduct the cost of the input. So remember, in the revenue maximization point, we say that this input level is given. So for each given, if X1 is already given, then we can find out the revenue maximization point. So when we are maximizing profits, then we are actually not giving X1 level. We actually have to find out which X1 level or which input level that will lead to profit maximization. So this profit maximization, it has to subject to this product transformation equation. So it has to be feasible that this input can output those two output levels. So again, what we can do here, this is a constraint maximization problem. What we can do is simply substitute this X1 here with this condition. So then we only have the output levels that will be the choice variables here. So in this variable, we actually have Y1, Y2, and X1. And that's a little bit more difficult to solve. So here we only have Y1 and Y2 to solve. And this is a unconstrained optimization problem. And for unconstrained optimization problem, you actually don't need the Lagrangian function and then try to interpret the Lagrangian multiplier. So here we have the unconstrained optimization, and the first order conditions is actually to set the partial derivatives of the objective function with respect to the choice variables, set those partial derivatives equal to 0. So we have two choice variables. One is Y1 and the other is Y2. And our objective is our profit. So we set the derivative of the profit with respect to Y1 and with respect to Y2 equal to 0. And we know how to do this. So in the profit function, these two are linear functions, so it's easy to find out those. And again, for the second one, this W1 and W2 means it's the partial derivative of this function, this product transformation function with respect to y1. So here is partial derivative with respect to y1, and here is with respect to y2, or you can write this x as your x1 here. So that's the optimality condition. So those two conditions will help you solve your profit maximizing points. And we can actually, again, by looking at that condition, it's difficult to tell what's the economic interpretation, and we have to rearrange terms a little bit, or write the terms in probably a different way so that the economic interpretation we're actually more familiar. So let me just tell you what we can write this condition, how we can write this condition, and then I will actually show you how we ended up there. So it turns out that this R1W1 is actually your marginal cost. So this is actually the marginal cost of Y1. So I have the subscript there. So this is a marginal cost with respect to Y1. And this is a marginal cost with respect to Y2. So from this condition, it is actually, the condition is actually saying that the price, the output price, has to equal to the marginal cost. So remember this, we write P1 here, this is actually under perfect competition in the output market. And if there's not perfect competition, this is actually marginal revenue. So marginal revenue of the first output is equal to the marginal cost of the first output. And you guys are familiar with this condition, right? Marginal revenue equals to marginal cost. So for the last infinitely small unit of the output produced, the return, the marginal return, MR, which is P1 in the perfect competition case. So the return on that infinite small unit of output has to equal to the cost of that infinitely small unit, and that is your marginal cost. So we have two outputs here, and there will be two conditions. For each of the outputs, the marginal revenue has to equal to the marginal cost. So let's actually say why this R1W1 is equal to the marginal cost. So here, first, this is the definition of marginal cost, and that is actually the derivative of the variable cost with respect to Y1. So again, this is also equal to a derivative of total cost with respect to Y1. And since the fixed cost, when you take derivative, it's equal to 0. So we can just use the variable cost and take derivative with respect to Y1. So what is your variable cost? So your variable cost is R1, X1. So again, you have to be careful here. In this course, we only cover the case of two outputs, one or single allocable input. When there's multiple inputs as well, then this is not your variable cost. This is actually similar to our case of when there's multiple inputs, one output. In order to find out the variable cost function, you actually have to solve a cost minimization problem. But that's a little bit too advanced for this course. So I only cover in this course two output, one allowable input case. I don't cover two output, two input case. So if that's the case, then it's not right to write the variable cost this way. But when there's only one input, then it's okay. So it makes our life much easier. So anyway, this is a variable cost. And this X1 we can replace with the product transformation function. And when we're taking a derivative, we can actually pull this R1 out because it's a constant there. So once we pull this R1 out, and we have this term, and what is the partial derivative of the product transformation function with respect to Y1, and we know what that is. That is actually the that is actually 1 over MPP x1 y1. So this partial derivative of this one is actually 1 over here. We can, this W is a function is actually x1. So this is actually 1 over MPP x1 y1. So that's how we get from this step to the next step. So okay, then this one we are familiar, and this is actually just R1 times W1. So we derived from here that R1 W1 on the right hand side is equal to MC1 on the left hand side. So that ended up becoming this condition. And similarly, you can also derive MC2 equals R1 W2. So although first this optimality condition is not familiar, or it doesn't look like it makes sense. However, after we derived the marginal cost for those two outputs, then we ended up with a condition that we're very familiar with since your elementary economics course, which is your marginal revenue equal to marginal cost. The only difference here is that we have two outputs. So the condition is the marginal revenue and the marginal cost of each of the output has to equal to each other. So when there's two outputs, there's two optimality conditions here. And we can actually also rewrite the optimality condition a little bit differently, and this will link to the revenue maximization problem. So what do I mean by that? So here we can actually rewrite this condition a little bit differently. So since we have this R1 W1 equal to P1, and this W1 can be written as 1 over MPP x1 y1. So we have this condition here. And we can move this MPP to the right-hand side after P1. And we ended up with something that we're very familiar, which is P times MPP. So the output price times the marginal physical product. And that is your MVP. So the marginal value of product. And we have this condition that MVP equals to R1. So this is, again, a different way of writing this optimality condition. And why am I writing it this way? This is because, so this is the first optimality condition, what we can get. We can also get the second optimality condition, which is P2 times MPP x1 y2 equals to R1, excuse me, so there's only one input. So once you write it that way, on the right-hand side it's the same, right? So those two must equal to each other. And let's actually take this slide, look at this slide. And you can actually say here, this is a condition for the output, for the profit maximization, and we can write it this way. So once we write it this way, this condition actually implies, so this error means implies, so implies that MVP x1 y1 equals to MVP x1 y2. So this is actually the condition for the revenue maximization, right? So again, here in the multiple output case, the profit maximization implies the revenue maximization. It is analogous to the two input case where the profit maximization implies the cost minimization. So those two are, again, very similar. So this is the revenue maximization condition. In order to maximize profit, you actually have to add one term here. So this whole condition is a profit maximization condition. And this condition here is a revenue maximization condition. So the profit maximization condition not only requires revenue maximization, but also it requires that this marginal value of product equal to R1. So R1 is actually the marginal factor cost here and marginal factor cost of X1. So under perfect condition in the input markets, then the marginal factor cost is equal to the price of the input. So that's the linkages between the revenue maximization and the profit maximization. Again, it's analogous to the optimal profit maximization when there's two inputs, and I actually went a little bit faster in this section when there's two outputs. And if you feel it is difficult to follow, then you probably should go back to the multiple input case. It's because once you are able to understand the cost minimization and profit maximization when there's two inputs, then you just need to change your mind a little bit for the multiple output case. So again, let's use the same example to derive the optimal, to derive the profit maximization. So suppose this is your product transformation function and you're given P1, P2, and R1. So the output prices of those two outputs and the input price. So those are all given, and you are trying to find a combination of output that will lead to profit maximization. So first thing first, where do you start? So you start with the profit maximization optimality conditions, right? So what's the optimality conditions? And it is actually the MVP X1, Y1 equals to MVP X1, Y2 equals to R1, right? So that's your optimality condition. And you actually, so here, this is P1 times MPP X1, Y1 equals to P2 times MPP X1, Y2, and this equals to R1, right? So we have already derived what's MPP X1, Y1 and what's MPP X1, Y2. So I'm not gonna repeat them here. So what you will get is that P1 over 2Y1 is equal to R1, and P2 over 2Y2 is also R1. So here you can actually derive that Y1 is equal to R1 over, actually I probably read it wrong, is P1 over 2R1. And from this condition, you can actually get Y2 is equal to P2 over 2 times R1. So those two are the output levels that will lead to profit maximization. And this condition, those two output levels will for sure maximize revenue for the X level. And it didn't only maximize revenue, it also maximized the profit. So what is the X1? What is the input level that was used? So this one you have to use the product transformation curve function. So this is Y1 square plus Y2 square, and this is equal to P1 over 2R1 square plus P2 over 2R1 square, and this is equal to 4R1 square. And on the numerator, we have P1 square plus P2 square. So this is the input level when the profit is maximized, and those two are the output level that will lead to profit maximization. So here again, I showed you guys how to solve this profit maximization problem when you have two outputs. So that's all actually for the multiple output production that I want to cover. Again, I will not cover when there's two outputs and there's two inputs, or if you want to put it another way, there's greater than two, multiple output, multiple input case. And that will I will leave that for a more advanced course.
And I will do the summary of the technical and economic aspect of production in next lecture.